Welcome. In this session, we'll see the relationship between discrete time Fourier transform and Z transform. Let's start. In this session, see what's the relationship between discrete time Fourier transform and Z transform. In other words, if Z transform is given, means if x of Z is given, how do we obtain x of omega from this? So if Z transform of x of m is given, then how do you obtain x of omega? Or if x of omega is given, how do you obtain x of z? That's the goal. Now we know that Z transform of a sequence, our signal is Z transform of a signal x of m is simply summation n varying from minus infinity to infinity x of m z to the power of minus n. And we know the discrete time Fourier transform of x of n is given as summation n varying from minus infinity to infinity x of n e raised to minus j omega. Now we know z in Z transform, we know z is given by r e to the power of j omega. So if we put it here, the Z transform becomes, so if we write it, so x of z will be summation running from omega x of n r e to the power of minus j omega n whole raised power n. And if we simplify this, I think it is minus n. This plus here, this is minus n. So this will be simply r to the power of minus n e to the power of minus j omega. Now have a look at the discrete time Fourier transform relationship and Z transform relationship. Please observe these carefully. Now, if we put r equal to, very important observation, if we put r equal to 1 in Z transform, so if we put r equal to 1 in Z transform, what will be happen to Z transform? This will be x of n, r is power minus 1 and r is 1. It will be 1 raised power minus n and it will be 1. So it will be simply g. Have a look at this expression and this expression. So Z transform is equal to the discrete time Fourier transform. So Z transform is equal to discrete time Fourier transform and R is equal to 1. This is very, very important relationship. So Z transform is equal to this discrete time Fourier transform when R is equal to 1. In other words, now what does it mean? In other words, if we replace Z, have a look at this expression. If we replace Z by e to the power of j omega, we'll get the discrete time. So if x of z is given to us, if it is given, simply put z equal to e to the power of j omega, we'll get the discrete time Fourier transform. So we'll get the discrete time Fourier transform of the series. All right. So we'll get the discrete time Fourier transform if we replace this z by e to the power. Now let me illustrate this concept. Please remember this. Now, if x of n is u of n, very simple example. Now we know that z transform of this signal. We know the z transform is x of z is simply 1 by 1 minus z inverse. If you remember this, when magnitude of z is greater than 1. So when magnitude of z is greater than 1, let's not worry about the ROC this time. Now, if we put z equal to e to the power of j omega, so if we put z equal to e to the power of j omega, that will be minus 1. Have a look at this. This is e to the power of minus j omega. Now, if you remember the result from previous expression, we know x of omega of u of n is also 1 by 1 minus e to the power of j omega. We have already done this example. Have a look at it. When we substitute z, when we replace z by e to the power of j omega, we get the discrete time Fourier transform. Have a look at these two results, these answers. So simply, in short, the point is, if we put z equal to e to the power of j omega, we will get the discrete time Fourier transform. Now, if we to how do we get the z transform of the sequence? How do we get the z transform from here? So simply, if x of omega is given, or in other words, if x of n is given, simply put, take the discrete time Fourier transform of, so if we take the discrete time Fourier transform of, instead of x of omega, Fourier transform of x of omega, we'll take the discrete time Fourier transform of x of n. From here, please pay attention. This will be simply summation n running from minus infinity to infinity, r to the power of minus n, x of n, e to the power of minus j omega n. Combining this term with this term, this will be n running from minus infinity to infinity, x of n, e of e to the power of minus j omega, this will be plus minus n, and we know this is z transform, and this will be z to the power minus n. So z trans x of omega becomes x of z. When we replace, this becomes x of omega becomes, so when we take the z transform of, sorry, discrete time Fourier transform, instead of x of n, we take the discrete time Fourier transform of x of n, r to the delta minus n. This is same as x. You can check it out. Alright, so this is the relationship between the discrete time Fourier transform and the discrete time. Now, one important implication of this, please remember, z transform is very easy to calculate compared to the discrete time Fourier transform. So mostly you will be given z transform, x of z will be given to you. Your goal is to determine x of omega, meaning discrete time Fourier transform. That's the goal. Simply replace z by e to the power of minus j omega, sorry, e to the power of j omega, you will get the discrete time Fourier. Alright, let me end this session here. In the next session, we will do the discrete time Fourier transform as an important pulse. Alright.